These are the lesson activities for lesson number 3 for college algebra. So let's say we want to graph the equation y equals 1 over x minus 2 by plotting points. At what value of x will we run into a problem? So if you try to plug in x equals 2 in here for x, you get a 0 in the denominator. So it turns out that the number 2 is excluded from what's called the domain of the expression. The domain of an expression is all the values that make sense or don't give you an error of some kind. So 2 cannot be in the domain because it would be division by 0, which is undefined. So we say the domain of this particular expression is the set of all x's such that x does not equal 2. So any other x except x equals 2. What is the domain of the expression square root x minus 6? So you can take the square root of 0, I've got a little reminder here, but you can't take the square root of a negative, okay? So I can plug 6 in. Yes, I can plug a 6 in because the square root of 0 is 0. So I can put 6 in. That's the smallest value I can put in. And then I can put anything bigger than 0 in for x as well. Because 7 minus 6 is 1, the square root of 1 is 1, for example. So I never include infinity, so I'm going to put a round bracket on the infinity, but I am going to include the 6 because I can take the square root of 6. Okay, number 3, you need to rent a rug cleaner. Company A will rent the machine you need for $22 plus $6 an hour, and Company B will rent the same machine for $28 plus $4 an hour. So model the cost to rent the machine using 2 equations. Use x to represent the number of rental hours and y to represent the cost. So Company A is going to be $22 plus $6 for every hour. So 6 times the number of hours plus 22. And then Company B is going to be 28 plus 4x. Write and solve an equation to determine how many hours of use will result in the total amount spent at each company being the same. So let's set the costs equal to each other because we want to know when the cost is the same. Okay, so we solve this. I'm going to subtract 22 from both sides and I get 6. Subtract 4x from both sides and I get 2x. Divide both sides by 2 and I get x equals 3. So 3 hours. The two costs will be the same. All right, so now we're going to fill in a table of values. Y1 is Company A and Y2 is Company B. And I'm just plugging in some numbers of hours here. I just did, well, let's just go ahead and do it in order. Okay, so when x is 0, I'm going to put 0 in for this x and 0 in for this x, and I'm going to get a Y1 and a Y2. So if I replace this x with a 0, this whole term goes away. So you have 22 plus 6 times 0, which is just 22. And if you put a 0 in for this x, you have 28 plus 4 times 0. 4 times 0 is 0, so you just get 28. All right, and then for y1, if you put a 1 in for x, you have 22 plus 6 times 1. So that's 22 plus 6, which is 28. And then remember, Company A, you just add $6 for each additional hour. So I can just add 6 a few times. So 28 plus 6 is 34, plus 6 is 40, plus 6 is 46, plus 6 is 52. And then Y2 starts at 28 and you add $4 every hour. So 28 plus 4 is 32. 32 plus 4 is 36. And 36 plus 4 is 40, plus 4 is 44, plus 4 is 48. Okay. So you want to use a table to find how many hours will result in the total amount spent at each company being the same, and what will the total amount spent at each company be. So when is it the same? We can see that it is after 3 hours. Okay, at 3 hours, they both cost $40. Which we had already determined algebraically, but now we also know how much they cost. Cost is $40 for both companies for a 3-hour rental. Okay, so now we just want to plot the points from the table on the axes. If you have a straight edge, use it to draw the graphs of y1 and y2. Okay, so let's see. y1 was 0, 22. So there-ish. Okay, and then it was 1, 28. It's like almost 30. And then 2, 34. 3, 40. And we're getting a straight line here. I'm going to try to just connect these with a straight line. Okay, so those points are connected. Now I'm going to work on y2. So that starts with 0, 28. And then we add 4 each time. So it's 132. 236, 340, 444, and 548. And then I'm going to try to connect these with a nice straight line. Okay, so I've got the two lines drawn in, and where do they intersect? They intersect at the point 3, 40. Right here. And interpret this point in terms of the context of the problem. So the 3 is the x-coordinate, and the x-coordinate here was rental time in hours. So it's helpful to label your axes. And then the y-coordinate here is cost in dollars. So 3 is a rental time, 40 is the cost. So at 3 hours, company A and company B both cost $40. So we've answered the same question 3, 4 different ways here. So moving on to number 4, a person lowers her hot air balloon by gradually releasing air from it. Let x be the number of minutes that she has been releasing air from the balloon, and let y be the altitude of the balloon in feet. Assume that the relationship between x and y is modeled by the equation y equals negative 200x plus 800. Find and interpret in the context of this problem the coordinates of the x-intercept of the graph of the model. Be sure to discuss the meaning of both coordinates and include all relevant units. So x-intercepts, that means we're looking for a place on the x-axis. And anytime you're on the x-axis, we don't know the x-coordinate, but the y-coordinate is 0. So I'm going to make y 0 and solve for the x. And then we'll just add the 200x to both sides. And then divide both sides by 200. And we get x is 4. So my x-intercept is actually 4, 0. And it means that when x is 4 and x is minutes that she's been releasing air from the balloon, so that means that after 4 minutes of releasing air, what happens? The y-coordinate is 0, and the y-coordinate is her altitude. So if her altitude is 0, she's on the ground. She lands the balloon. Now we want to find and interpret in the context of the problem the y-intercept of the model. So a y-intercept, we're looking for a place on where the graph crosses the y-axis, and any point on the y-axis has an x-coordinate of 0. We don't know the y, but the x-coordinate is 0. So I can just make the x variable in the problem 0 and solve for the y. So I have y equals negative 200 times 0 plus 800, and we get y equals 800. So my point is 0 comma 800, and it means that when she starts releasing air, when she decides to try to land the balloon, that when she starts releasing air, the balloon is 800 feet up. The altitude is 800 feet. Use the following window to label the axes below. So they've given us a window, and remember this means x min, x max, x scale, y min, y max, y scale. So the smallest x to the biggest x, it should be negative 16 to 16. So that is the left and the right. Oops. And then my tick marks should have a length of 4. That's what that 4 means. So negative 16 to 0, I can fit 4 sets of 4 in there. And then that would be 8, 4, 12. So there we go. We've labeled x going from negative 16 to 16 by 4s. And then y is going to go from negative 10 to 10 by 2s. So let's see. 8, 6, 4, 2. It's not perfect, but it's good. 2, 4, 6, 8. Okay, now we want to use our window notation to write the window that we would use if we were going to graph this. Okay, so x, we can start in 2000. So we can go from, we can let 0 be the year 2000. Let's do that. Okay, so I'm going to put x should go from 0 to 2010. That would be year 10. So we would go to 10. And I'm going to go by ones just because we can show every year. And then y, let's see, the smallest y might be 3,000. And then the biggest y is 7,020. To make sure we can see it, I might go to like 7,500 or 8,000. And I'm going to go by, this particular graph goes by 400. And that looks like it works pretty well. Okay, determine whether each statement is true or false. If it's false, make the necessary changes to produce a true statement. If a point is on the x-axis, it is neither up nor down, so x equals 0. So this is false. It's y equals 0. Okay, anytime you're on the x-axis, draw yourself a little picture, put a point on the x-axis. That point went right, but it didn't go up or down. So the x-coordinate we don't know, but the y-coordinate is 0. If a point is on the y-axis, then x equals 0. That is true. Draw yourself a little picture if you need to. Put a point on the y-axis. The x-coordinate we don't know, and the x-coordinate is 0, right? It did not go left or right. The y-coordinate we don't know. And the ordered pair 2, 5 satisfies the equation 3y equals 2x minus 4. Well, let's see. If I do 3 times the y-coordinate, and I want to know, does that equal 2 times the x-coordinate minus 4? So 3 times 5 is 15. 2 times 2 is 4. Minus 4 is 0. Those are not equal, so this is false. Okay, so we could either just say the ordered pair 2, 5 does not satisfy the equation, or we could try to change it. Let's see. Let me see what happens if we reverse the ordered pair. If I did 3 times 2, does that equal 2 times 5 minus 4? Yes, this is actually true. 6 equals 6. So to make it true, we would say the ordered pair 5, 2. That would make it true. Okay, finally, we're going to end with some qualitative graphing. Match the story with the correct graph. So an airplane flew from Boston to Miami, and we've got the plane's height on the y-axis, and seconds after takeoff on the horizontal axis. So it seems like the plane should fly most of the trip at the same height, right? At takeoff and landing, its height is changing, but for most of the trip, it's flying at sort of a constant height. So I can eliminate this first one. It's not just getting higher and higher and higher, right? It goes up, it stays at the same height for a while, and it comes down. Okay, so that eliminates C as well because it never comes down and lands, and it didn't start on the ground. So we can eliminate that. It's got to start on the ground, and it's got to come back down to the ground. So D has it jumping in 0 seconds, right? From 0 to cruising altitude with no time whatsoever. And same thing for landing. So it's going from cruising altitude to on the ground with 0 time passing. So that seems impossible. So we're going to go with B. Okay. B, it has sort of a gradual increase from being on the ground up to cruising altitude. It stays at cruising altitude for a while, and then it gradually comes back down to the ground. Okay, next scenario. You begin your bike ride by riding down a hill, then you ride up another hill, and finally you ride along a level surface before coming to a stop. All right, so when you go down a hill, so you're beginning a ride down the hill, so your speed is going to get faster and faster and faster. So it's tempting to choose A because this looks like you're riding downhill, you're riding uphill, you're riding level. But this, if this were your height above like the ground level, this would be true, but it's not your speed, right? Your speed doesn't slow down, right? When you're going down a hill, your speed speeds up. So I can eliminate this one and this one because you're going downhill, so you're going faster and faster and faster. So faster and faster and faster, faster and faster and faster. Then when you ride up a hill, you're probably going to slow down when you're riding up the hill. So you get to the top of the hill and then you get to the bottom of the hill and then you're riding uphill and you start to slow down. So this one you're going faster and faster and faster, and then you're going slower and slower and slower until you stop for this graph. This one you're going faster and faster and faster, then you're going slower and slower and slower, then you go a steady constant speed for a while, then you slow down to a stop. That sounds like the description of what happened here. Okay. This one doesn't have the level surface steady speed portion, so we choose this one.